Good day, everyone. I am Engineer Desolo of PATTS College of Aeronautics, and my research title, Comparative Analysis of Beam Cross-Sections for Enhanced Bending Stress Capacity. For my background of the study, understanding the behavior of various beam profiles has advanced significantly throughout the history of structural engineering. At first, choosing a beam cross-section was largely based on empirical knowledge and had limited analytical capabilities. However, because of recent developments in technology, computational tools and numerical analysis methods like finite element analysis, researchers are now able to carry out in-depth analysis of the behavior of different beam profiles. For the specific objective of my study, first, conduct a comparative analysis of bending stress capacities. Compare and contrast the bending stress capacities of the I-beam, rectangular beam, circular beam, and T-beam, four widely used beam profiles. Second, evaluation of each cross-section performance. Analyze each beam cross-section's performance under various loading conditions. Last, identifying differences in bending stress capacities. Identify and examine the differences in bending stress capacities among the evaluated beam cross-section. For my conceptual framework, the integration of two key methodologies, the extensive numerical simulations and analytical computations, forms the conceptual framework we study. Researchers can completely evaluate the performance of the beam cross-sections and make insightful comparisons between them by integrating these advanced techniques. For my research paradigm, I am using the input process output. For my input, the geometry and the material properties of beam cross-sections, and the different loading conditions as well. For my process, utilizing numerical simulations and analytical computations, then integrating and comparative analysis of those solutions. For my output, comparative analysis and performance assessment, and of course, the factors influencing the performance based on the performance assessment. For my research methodology, my research design, I'll be utilizing the quantitative design for comparing bending stress and structural behavior of beam cross-sections using assumptions and selections, simulations, and analysis. For my data collections, geometric dimensions and material properties are assigned and selected for I-beam, rectangular beam, circular beam, and T-beam. Standardized dimensions and material parameters are used. Instrumentation, I utilize the finite element analysis, simulate cross-sections behavior using mesh elements. Also, analytical calculations using the Euler-Bernoulli beam theory cross-verify simulation results. For the statistical treatment, descriptive statistics using mean and deviation were used to summarize bending stress. Analysis of variables, or ANOVA, used to assess significant differences in bending stress capabilities. For the loading conditions, various loading conditions will be used for testing. Concentrated loads ranging from 10 to 30 kilonewtons, uniform distributed load of 20 kilonewton per meter, and the combination of these two loads. Then, the finite element analysis assumptions, standardized dimensions and material properties for each beam type, assume concentrated and uniform loads accurately replicated in simulations, which I use also in my computations. Now, for the summary of findings, conclusions, and recommendations, for the findings, for the I-beam, it shows stable trends in bending stress behavior. They are also excellent under mixed loading situations. For T-beams, it demonstrates predictable behavior, unique transition from compression to tension under certain conditions. For circular beams, it is consistent with pattern of rising bending stresses. Good resistance, so uniformly distributed loads. For the rectangular beam, they have lower bending stress capabilities under all loading circumstances. For the ANOVA results, we have significant differences in bending stresses capabilities among beam cross-section, with p-value less than 0.05. For the computed means, I-beam generally has higher bending stress means compared to T-beam, which has lower bending stress means. Circular and rectangular beams vary based on loading conditions with regards to their computed means. For the conclusion, based from the findings, For the I-beam, they are suited for structures with complex stress distributions. They are also excellent under combined loading scenarios. For T-beams, they are suitable for linear stress increase. However, transition from compression to tension under specific conditions. For circular beams, they are effective under uniformly distributed loads. They are manageable with increase in bending stresses. For the rectangular beams, they have limited bending stress capacity, particularly under concentrated loads. Recommendation for the I-beam, recommended for versatile applications. They handle complex loading scenarios well. For the T-beams, caution need due to tension compression transitions. Careful design strategy will be required. For circular beams, suggested for applications with evenly distributed loads. For that reason, they are weight efficient under this condition. For the rectangular beams, use with caution, particularly under concentrated loads. Now, some of the recommendations for aircraft parts design based on the recommendations as mentioned before. We have two I-beams. They are ideal for aircraft parts requiring robustness and versatility. Circular beams. They are suitable for lightweight aircraft components that demand uniform stress distribution. Recommendations for future studies. Exploring other cross-sections. We need to study a wider range of cross-sectional shapes such as channels, beams, and box beams. Also, we need to incorporate different stress types. We need to include axial loading, torsion, shear stresses in the analysis. For the aircraft component design, consider also aerodynamic loads, vibration, fatigue in aircraft part design. For the materials and manufacturing methods, we need to study impact of materials, manufacturing process, and cross-sectional behavior. Uh, Multidisciplinary approaches. We need to collaborate across disciplines for innovative design, not only for structural engineering. And real-world validation. We need to validate recommendations through physical testing and simulations. Here are some of my sample references. And thank you. I'm Engineer Dennis Desolo of PATTS College of Aeronautics.